approximation is a method that they want us to learn. It had a lot of usefulness at times when there were not calculators. Because if you imagine finding the square root of 1.1 without a calculator, that was very difficult to do before we had calculators that would do square roots. Which really, in the grand scheme of things, was really not all that long ago. Here, so a couple things we're going to look at are things like example 1, where we are using linear approximation to find something the calculator would basically already do for us. So it may seem a little obsolete that we are doing that, but it's still a good practice to learn the thought behind. And then we're going to look at some other situations where we have to use linear approximation because we don't know the original function. We can't just plug the number into the original function. Okay, so in those cases, because we don't know the original function, linear approximation is the best that we can do. So here's the idea behind linear approximation. We have to find the linear approximation to f of x equals square root of x at x equals 1 and use it to approximate square root of 1.1. So if we think of the graph of square root of x, if we graph it, square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. So you've got this graph right here. That's our square root of x. And so if we're wanting to find I'm going to zoom way in here so you can see it really big. What we want to find is f of 1.1. Well, 1.1 would be like right here, right next to that, right? It's going to be really close to that point, but not exactly. So if we are doing this without a calculator, we can't type the square root of 1.1 into our calculator. We're pretending we're in the olden days where we couldn't do that. But if I draw in a tangent line at that point right there, I can plug numbers into a line really easily because it's just some simple multiplication and addition, right? It's not square roots. So I can plug a number into a tangent line really easily. At 1.1, is that going to be pretty close to what we're looking for? Pretty close, right? It's not exact. In this case, we can see that red dot, which would be our approximation, is a little high, but it's going to be pretty close. So we could use this method to approximate. Now, would it make sense to approximate f of 3 using this line? At 3 over here, the further you get away from your point of tangency, the worse the approximation is, right? So at 3, my approximation is not all that great anymore. But as long as I'm close to my point of tangency, it's still pretty close to the actual value of that function. So what we're going to do for these is a pretty basic idea. We're just going to find the equation of this tangent line. So we haven't done tangent lines in a while, but you guys were really good at them when we did. What do we need for a tangent line? F prime of the point, and so f prime is going to give us the slope of that tangent line, right? So like for this, if we take f prime of x, we will get, that is like x to the 1/2, so we get 1/2 x to the negative 1/2, which is 1/2 square root of x. Okay, so we've got our derivative. What point do I need to plug in? What's my point of tangency? 1. So I'll do f prime of 1, which is 1/2 square root of 1, which is going to give us 1/2. That's our slope there, right? A derivative gives the slope of the tangent line. All right, so it's part of what I need for a tangent line. What else do I need? F of 1 is what I want to see, which is not our y-intercept, although you eventually could find the y-intercept if you need to. But we just need a point on the line, so that point of tangency is what you want. So F of 1. That's just plugging into the original equation. And see, 1 is okay to do because we know the square root of 1 is 1, right? So for this particular problem, you would only want to use values where you knew the square root. 1, 4, 9, and so on, all right? So that tells me my point is 1, 1. So this is where we use that y equals m times x minus x1 plus y1. So our tangent line is going to be y equals 1/2 times x minus 1 plus 1. If you want to simplify this, you can, or you can leave it like it is. I think I'm going to leave it, but you can simplify it if you want. So this is the equation of this tangent line that I have right here. All right. So what I can do now, if I want to approximate the square root of 1.1, I could say f of 1.1, I'm going to use the squiggly equal sign because it's not exactly what I'm about to get. It's approximately what I'm about to get. I'm going to do 1/2 times 1.1 minus 1 plus 1. So that would be 1/2 times 0.1 plus 1. And if you go decimals here, 0.5 times 0.1 plus 1 is going to be 0.05 plus 1. So we get 1.05. Now, if we type square root of, obviously we have calculators, so if we need to know square root of 1.1, we would just type it in like this, and we get 1.04881, which is pretty close to 1.05, right? You know, in a world without calculators, 1.05 would probably be close enough for a lot of things that you would be doing if you needed that value. So when you see the phrase linear approximation, that means to find a tangent line and use it to approximate. There's a lot of different ways that they might ask for this. It might say linear approximation. It might say locally linear approximation. It might say use the tangent line to approximate. But those are all phrases that you might see. And what it means is to find the tangent line and then use that tangent line to make your guess. And it's going to be close, but not exact. Okay, questions? All right, so if we're asked to approximate square root of 8 using linear approximation. Okay, this is basically the last problem that we just did, but we got to make a few more decisions here because the last problem told us what value of x to use. It told us the function here. So for this, our f of x is still just the square root of x, right? what value should we use for our tangent line here? What x value? 9. It's the closest we can get that we actually know the square root, right? So we're going to look at x equals 9. So you're going to pick the value closest to the one that you're looking for that you can actually calculate without a calculator, because this would be like calculator inactive sort of situation. All right, so if we want to know a tangent line, we got to have two things. We need our point and we need our slope. To find our point of tangency, what are we going to plug into? For your point, you're just plugging into the original function. So for your point, you're just doing f of 9, which is the square root of 9, which is 3. All right, so for that point on the line, anytime you need to know a point on a graph, you just plug it into the function and see what y value you get. So this is going to be the point 9, 3 is our point. So once you have a point, which it really doesn't matter the order that you do this in. We did the slope first last time. To find the slope of a tangent line is given to us by the derivative of the function, right? We already found this derivative in the last problem. F prime of x is 1/2 x to the negative 1/2, which ends up being 1 over 2 square root of x. And we are looking at x equals 9. So f prime of 9 is going to be 1 over 2 square root of 9, which is 1 over 2 times 3, which will give us 1 over 6. We're okay here. All right, so for our tangent line, we would have y equals 1/6 x minus 9 plus 3. And so if we're looking for f of 8, it is going to be approximately, right, because if we're doing this without a calculator, we can't just type in square root of 8. We're doing 1/6 times 8 minus 9 plus 3. And so we got 1/6 times negative 1 plus 3, so negative 1/6 plus 3 is going to be, let's see, that is going to be negative 1/6 plus 18 over 6. So you get 17/6 is your approximation. So square root of 8 is approximately 17 over 6. And let's see how close it actually is. Let's step into the modern age where we do have calculators. 17 divided by 6 is 2.83 repeating. So the square root of 8 is 2.828. So we're finding, like, with these, we're within, like, it rounds to the hundredth being the same, which is pretty good depending on how precise that you need to be. Okay, so one thing that we're going to be very concerned with is whether or not our estimates are high or low. So, if I have this graph right here, and I have this point of tangency right here, and that blue line is my tangent line. Are the estimates that I get using this blue line, is it going to be an overestimate or an underestimate? Overestimate. And we know that because that blue line is above the actual graph that we're looking at. What about example 4? That's an underestimate. Okay? So, this all depends on concavity. Okay? Not increasing or decreasing, but concavity. Because if the graph is concave down, so let's think about it. Sometimes I still have to draw this out. I've got a graph that's concave down. If you draw in tangent lines for me on a concave down graph, no matter where you put them, what's happening with those tangent lines? Are they above the graph or below? Above, every time. So, if the graph is concave down, the estimate will be an overestimate. So, sometimes I forget which one we're dealing with here. So, if you draw a concave down graph and draw in your tangent lines, all those tangent lines are above the graph. And if they are above the graph, that means the tangent is higher than the actual, so it's an overestimate. Similarly, if you have something that's concave down, if you draw in tangent lines at any point, doesn't matter whether it's increasing, decreasing, whatever, those tangent lines all fall below the blue line, right? So if the graph is concave up, then the estimate will be an underestimate. So it is very common to see these problems, particularly on the free response section. And a lot of times there will be, sometimes it'll all be in one question. Sometimes it will be two separate parts. It'll ask you for a tangent line and maybe the approximation in one part, and then in another part it's going to ask you, is it an overestimate or underestimate? So when it's asking for overestimate or underestimate, you need to know about concavity of the graph. And that will tell you which one you're dealing with here. So let's look at example 5. Now, in this particular case, in a world without calculators, it might still be easier just to plug in 2.1. But we're learning about linear approximation, so we're going to do this problem using linear approximation. So, given f of x equals 3x squared plus 4x minus 2, use linear approximation to approximate f of 2.1. So, first of all, we've got to decide what value of x we want to use for our point of tangency. What would you guys suggest? 2. So, we're going to be looking at x equals 2. So, for our point, let's see, Braden, what have we got to do to find our point of tangency? Derivative, we can, but that is not going to give us our point on the line, but our slope, right? So, if we take our derivative, what are we going to get for that derivative, Braden? And then how do I find the slope at x equals 2? F prime of 2. And please make sure you're labeling everything as you do this. Sometimes, especially whenever it's a more simple problem like this, we tend to get lazy and skip steps, but make sure you're labeling that f prime of 2 to show you plug 2 in. Now, as far as showing every step, showing that you simplified, that's not necessary, but labeling f prime of 2 is. All right, so our slope is 16. We also need our point. Paul, how do we find that point of tangency? 2 into the original, so we've got f of 2 would be 3 times 2 squared plus 4 times 2 minus 2. That's going to give us, do your exponents first. 2 squared is 4. 4 times 3 is 12 plus 8 minus 2. So that's going to give us 18. So 218 would be our point. Everybody okay here? All right, tangent line. At x equals 2 is going to be y equals 16 times x minus 2 plus 18. Now, we are going to actually evaluate this, but if this is a free response question, particularly if it's calculator inactive, it is acceptable to do this. F of 2.1, 16 times 2.1 minus 2 plus 18, and leave it there. So on an FRQ, you could stop here. As long as the only operations left for you to do are add, subtract, multiply, divide, exponents, you can just stop, right? So that could be it. Now, on your homework, you know, for us, I want us to go ahead and actually figure this out because, you know, a lot of that not simplifying is good for the AP exam. When you get to college, there's a good chance that your professor is not going to let you leave your answer like this, depending on who you have. They might require you to simplify it all the way down. So it's just an AP policy that you don't have to simplify. So it's good for us to go ahead and do this. So we get 1.6 plus 18, so we get 19.6 is our approximation. Okay, questions? Okay, so our next one, here's an example of something they like to do on the AP exam. F of 4 is 6, f prime of 4 is negative 2. Use a line tangent to the graph of f at 4 to approximate the value of f of 4.5. Okay, sometimes it feels like you don't have enough information for this, but these are actually pretty simple, right? Because for a tangent line, we need a point. Raven, what is our point? Very good. I know you feel like you need to do something, but it's already there. So 4, 6, your point comes from finding f of 4. Then you need your slope. Hallie, what's our slope? Negative 2. You wouldn't necessarily have to write this out because it's given to you. So your tangent line is going to be y equals negative 2 times x minus 4 plus 6. And then for your approximation, f of 4.5, squiggly equal sign because it does not equal this exactly. Negative 2, 4.5 minus 4 plus 6. And then we're going to simplify here, 0.5. plus 6, so that's negative 1 plus 6, so we get 5 as our approximation. I like these because there's really some basic math on these, not a lot of difficulty level there, as long as you recognize what it's asking you to do. Okay, here is an example of something that we might be given in a sort of free response sort of situation. So, in 2010, the population of a small town was 4,500. The population of the town is given by the twice differentiable function p of t, where t is measured in years since 2010. Selected values of the derivative of p prime of t, are given in the table below. It is known that p prime of t is strictly decreasing over its domain. What's that mean when it says strictly decreasing? That's like saying always decreasing. It only decreases. So you're never seeing an increase for p prime. All right, so use the tangent line to the graph of p at t equals 0 to estimate the population of the town in the year 2012. Okay, so what does p of t stand for here? It's population, right? So p of t is population. But we're not looking at p of t. We're looking at p prime of t. What's p prime of t? It's your change in population. So like this right here would be measured in people per year. So at t equals 0, the town is gaining 210 people per year. Okay, so it's important to distinguish what you're looking at here from the beginning so you know what to use. So we need a line tangent to the graph of p at t equals 0 to estimate the population of the town in the year 2012. So, we're looking at t equals 0, so we need p of 0. What is p of 0? It is 4,500, because that would be our population in the year 2010. That's when t equals 0, and that's given to us in that first sentence. So that's our point, 0, 4,500 is our point. Now we need our slope. So that would be p prime of 0. What is p prime of 0? 210, we're reading it from the table. So we've got y equals 210 x minus 0 plus 4,500. All right, so we want to know year 2012. What number do I plug in? 2, right? So P of 2 is approximately 210 times 2 plus 4,500. And that's 420 plus 4,500, which would be 4,920. There was a problem like this on your test whenever you're looking at your test corrections for the FRQs. The very first question, part A, was a problem like this. You do not have to correct that. I put an X through every one of them. It doesn't mean you missed it. It just means I didn't count it. You'll see that first FRQ